The topic will be about it says technical guide for DCAC ratio, but I would say it's about discussing what can be the factors that can affect DCAC ratio in today's PV plants all around the world, and also especially in Greece. In Greece, yes. So just a recap from the previous webinar, which was about string design. As we know that the string design is based on mostly electrotechnical parameters. So the first one is how many modules should be in a string. So it means that we have to calculate what would be the maximum DC input voltage for the system. And I don't want to go into details. It is really just a recap. So like going again on the same topic. But this is the formula that we use here, how to calculate. I think it's pretty well known. And the first one is how to calculate the maximum number of the panels. So we have to calculate with a corrected open circuit voltage for the panels, and we have to divide it by the maximum DC voltage permitted, either by the modules or either by the inverter. Which one is the smaller one? In usually the case for the 1500 watts is that both modules and inverter supports the same voltage. And for the next one is how you can calculate the minimum number, which depends on the startup voltage, and usually this value will be the startup voltage, and the open circuit voltage will be the lowest during the summer. And it was also mentioned that in the new standard, so the previous standard was a basic design concept based on the 62548 IEC standard, but there is the new one, which consists the new design guidelines, the 62738, which also says you don't have to take into account the lowest temperature ever recorded, but more like an average or a mean data. And also you should be evaluate the cell temperature and also the open circuit voltage for different irradiances, as probably you already have seen in some panel datasheet that for different irradiances the open circuit voltage will change, not significantly as you want to expect from as you would expect for the current and between the irradiance, but there is some change between the VOC and the irradiance. So this is how you calculate how long one string can be. Because it is connected in series, it means that the voltage adds up. So this is why we have to think and calculate the voltages when we think about panels connected in series. So this will be the limit, because the current will be the same no matter how many panels we connect in one string. So the other design limitation of any inverters in the world is what is the maximum short circuit current for 1 MPPT. That will be the similar limit what we discussed previously for the VOC, which is the maximum DC voltage input. Now, if we think about how many strings can we connect in parallel, so it means that the current will add up. So we have to calculate the resultant short circuit current for each strings. So even if we have 4 panels connected or 5 panels connected in one series, and we would have 2 strings at 1 MPPT, the resultant current will be exactly the same for the same panel if we would use 27 or 28 panels in one string. So by this, if we check one panel datasheet and we see that the short circuit current for this exact panel datasheet for this exact panel is 11.22, it means that if we have 2 strings in parallel, it means that the resultant will be 22.44 amps. and for three strings, we will have 33.66 amp. So to compare the inverter, from the inverter side, we have to take into account the maximum short circuit current per MPPT. If this maximum short circuit current per MPPT for the inverter is larger than what we have calculated for the panels, it means that we are good to go. So these are the two design limitations of an inverter. This is the limit that nobody wants to reach, because it can damage the inverter. So it's better not to reach any of these value: the maximum short circuit current per MPPT and the maximum input voltage. So this will actually define what will be the maximum and the minimum number of panels in one string, and what is the maximum strings per MPPT. So and we already discussed that DCAC ratio will not wear off the inverter. It will just quickly set the working point, the working point of the whole system to a different level. If we want to have less power than available here, the inverter will set its working point to this, or it will set to this. It's depending on in which stage at the moment we are. And also making higher or different DCAC ratio will mean that the inverter will run with a longer period. So like the nominal power probably reached at sooner of the day. But if you imagine that you have, for example, you have approximately 2,500 2,500 hours of sun around the sea area, and you place an inverter there. But if somebody buys the same inverter and they would place that inverter in Northern Africa or in the Sahara, where the sunny hours, the hours when the sun is available and the sun is shining, is so much higher, that actually it will have the same effect on the inverter, that the DCAC ratio is changed. Even though the DCAC ratio probably is even lower than in the Mediterranean Sea area. So it means that the inverter is designed to cope with such higher working loads, working hours, because the same inverter is used in the north, in North Germany, and the same inverter is used in the Sahara. But in the Sahara, obviously, the inverter will operate with with higher hours. So this is why the DCAC ratio is actually no problem for any of the inverter. So let's look at the idea of the so-called optimal DCAC ratio. So DCA, just to begin with, the DCAC ratio is the connection between the inverter AC output at design temperature and the PV panel's DC peak output. So if you would imagine that you have the same PV panel peak power as the same as the inverter, it means that the inverter will never have to work at highest power, but probably the power from the DC side will be always lower than the AC power of the inverter. If you have a DC-AC ratio lower than 1, it means that most of the power which would be available from the inverter is not used, but some percentage is left out. So it will be undersized, so someone would say. If we would have an oversizing for the DC-AC ratio, there will be some moments during the midday, so during the mid 12 between 11 and 1 or 2 p.m. There will be some cases when the power will be limited, not limited, but the power will be maximized, so capped, because the inverter AC output is certainly a limit. So at that time, the available power will not be used in those conditions. But all the other times, like for example, during the beginning of the day or the end of the day, there will be an extra yield, there will be an extra energy due to the oversizing. And not only this, there will be some cases, for example, in autumn or in the during the fall, that that even with DCAC ratio 1, you would get this curve, because at that period of the year, at that season, there will be no extra power available from the DC side. But if you have an oversized DC AC ratio, you will have this power. There will be no clipping. There will be no so-called losses on the inverter. So, optimal DC-AC ratio. So I want to tell you now that unfortunately DC-AC ratio, there is no secret best match for any PV plants in the world, unfortunately. So it's always has to be calculated case by case, and unfortunately the the DC-AC ratio, or it is the optimal DC-AC ratio, is not just a technological question, but more likely an economical question, because usually PV plants are investments. So it means that the investor would like to have the best return of investment on that asset. So that's like a goal. So during the design, we have to follow the similar approach to look for the best investments and the most feasible investments in some terms. So during that, for some projects, for some auctions, some of the prices, for example, the power purchase agreement price. So for what price the operator will buy my energy is not realized just after winning. So the the return of investment ROI cannot be calculated during the design, because the price is not available. So we have to find some number which can be used as a comparison and to evaluate between different kind of technologies, different kind of prices used for the PV panel. So for this, usually the industry uses the so-called LCOE, which stands for levelized cost of electricity or levelized cost of energy. So this can help us to differentiate between different technologies and configurations. So the first definition is obviously the DC-AC ratio, where the peak power is divided by the AC output power at design temperature. Because in some cases, the temperatures are lower, so the inverter AC output, no matter what kind of inverter AC, even inverter, the AC output will depend on the ambient temperature in some way. As I mentioned, an example in the Sahara, usually the temperature is quite high, so probably you don't want to take into account the same temperature as somebody uses in Poland or in Russia. The next definition is the LCOE. It's quite complicated equation, so I don't want to go into details. Basically, we have to divide. That is, the LCOE is equals the total life cycle costs, so all the costs that is incurred during the whole life of the power plant, including capex, so capital investment, operational costs, and also some financial, so depreciation and taxes and so on. This is calculated as total life cycle cost of the power plant. It is divided by the total lifetime energy, so the energy supplied to the system, which can be sold. This is how it's calculated, the LCOE. The third definition is similar to the return of investment, but it takes into account the time. The one is the internal rate of return, which is actually just a discount rate at which our investments in the future and the net present value of our investments will be zero, and you have to calculate the discount rate, so you can quickly compare different kind of investments, and you could see that if the internal rate of return is higher for the other, it means that probably that investment is better. Okay, so let's see the methodology. As I mentioned, that it will not be about 100% calculation here, but it's like I would like to tell you what can be the way, what can be the points that you can use or methodology that you can use during the evaluation of power plant. For some cases, probably some information might not be useful because it cannot be used for some power plants, but I think in general these terms applies for all. So the first step is we have to define the boundaries. That, for example, what is the design temperature, what can be the commission time of the power plant. Let's see what is available land in that area. What are the discount rate for that country or in that economical times. And it's important that at this stage, those factors mentioned by the DSOs should not be taken into account. It will be a separate last step. So after the whole process, we can take into account the grid requirements. So we have the basic data, and now we collect the geographical information. What is the deviation between the height of the land, and whether there are any seasonal variation. For example, there is very cold winter but very warm summer, or for example there are high breeze, high wind, which can also affect the temperature of the panels. So all these data, and also the number of the hours of the sunny days or the sunny hours during the year, which is one of the important factor, and also yearly temperature. What is the temperature of that site? And then we can collect these end-to-end information, like what are the key components, like the module devices, trackers, inverter, transformer, cable, and also like the labors for the transmission, and also the power plant controller. So we have to collect all these data, all this information. Then after we know this, we can design based on the previous information. We can design at first a general string design, like rack and module orientation, for which I suggest to check the one of the other FusionSolar webinar, the string design and configuration. So after you have go through all the points at that webinar, you probably already done with this point. Then we have to calculate the SCOE as the function of the DCAC ratio, using the equations mentioned at the first and the second equations. So the DCAC ratio and the SCOE equation. Then we have to draw or plot an LCOE DCAC ratio diagram, for which we have to check what is the optimal DCAC ratio. After you have done this, we can focus on the grid requirements. Usually these grid requirements are reactive power requirements. I think this is also like a hot topic in Greece at the moment. So for certain power plants, not for all, but for certain power plants, depending on the size. So after this, probably the best DCAC range is already found. So let's see just a quick case study for this. So I don't want to go for all the details, but this power plant, I think it's located in Spain. This is just a regular example that for this case study, we used a bifacial module, 440 watt bifacial module, a single axis tracker with a portrait design. And for the inverters, obviously, we use the 185 kTL H1 inverter. And we have the boundary informations. So we also know some financial characteristic of the power plant. And we also know the OEM costs. We also know the labor cost. And using all this data, we can actually calculate based on the previous equations, we can calculate the LCOE. So first, just like a precondition is that we have power factor 1. It means there is no regulation from the DSO side. And using the PV syst, we can simulate the specific generation, the specific yield for different DCAC ratio. We could see that there is a sharp drop just after 1.3 DCAC ratio that indicates that the clipping loss is becoming higher at this point. So it means that even though the DCAC ratio is changed, probably it doesn't give you any return. So the capex calculation, it is also shows a negative figure. It means that if you change the DCAC ratio, due to the fact that the AC part is fixed, so transformer station will not cost less because you have a different DCAC ratio. Also, the inverter will not cost less because you have more or less DCAC ratio, DC power. But the DC, so based on this, the specific cost based on what peak will be lower for higher DCAC ratio. And as the two previous diagram had different negative and positive figures, it can be plotted, and there will be an optimal for the LCOE, the previous means. And in this example, for the Spain example, we have the optimal point is 1.32 as the optimal DCAC ratio. And just some optimal DCAC ratio around the world. It mentions also Greece, although I know that in Greece so it's not about it doesn't take into account any local regulation. It only takes into account local labor prices. We took into account the module prices and the tracker and inverter prices same as before, but all the other costs like the financial characteristic and the labor costs are depending on local workforces, and this doesn't take into account any grid requirements or local specification like the one in Greece where the DC power is the limited. So this is limited by the authority. This only says that which would be the best DC-AC ratio if we only focus on LCOE. It means that using these kind of DC-AC ratios, we will have the lowest price energy available from that power plant. So it's strictly about a local geographical and local financial characteristic of the power plant. So as you can see, the horizontal irradiance, which is one of the important factor for how many energy can be harnessed from the sun, is quite different for all in the world. And for example, if you take this Golmund, where approximately 2,000 kilowatt hours per each quantum meter it gets. The DCAC ratio is 1.13. And let's take the Rajasthan, India, where almost the same horizontal irradiance can be achieved. The ground is also the same sand, also in Rajasthan, the same sand. But the DCAC ratio is 1.45. So let's look behind it. What can be the effect? I mean, why, if we know that there is no effect from grid requirements, no effect from local authorization, it is just based on information of local labor forces and geographical data. So what can be the factors for the DCAC ratio? What can change the DCAC ratio? Now, I can mention first the temperature. As we have checked the two examples, Rajasthan and Golmund, China. For those two places in Rajasthan, the ambient temperature is quite high. It means that around 40 or 50 degrees of Celsius. So because of the high temperature, the DC power of the panels will degrade, because there is a negative coefficient between temperature and the power of the DC panel. So if you want to have the same or the lowest LCOE for high temperature area compared to low temperature area, because in Golmund the ambient temperature is 10 degrees Celsius, not 50, it's not 40. You have to use for the higher temperature area a higher DCAC ratio, just because the DC power will degrade during most of the time of the year. Another important factor is air circulation. Air circulation means that how the wind affect the panels. It's a bit hard to take into account, as we usually rely on empirical calculations and equations, but certainly it will affect, and it can affect the DCAC ratio. The other one is the irradiance. So if we have higher irradiance and we have good temperature conditions, it means that probably we don't have to use that high of DCAC ratio. Also, the supporting structure, so whether we use tracker or whether we use fixed structure, if we only just focusing on the same LCOE, between the tracker and between the fixed structure, with the fixed structure, usually in absolute value 0.01 extra DCAC ratio can be calculated compared to the tracker system, because the tracker system will have a more flattened graph of daily yield compared to the bell characteristic of the fixed structure. And also albedo is affecting these DCAC ratio. The other one is comes from the capex, the capex and the opex. So if the DC components, the DC panel prices will drop, it means that it will certainly change. It can certainly affect the DCAC ratio. So just imagine that the PV panel price will drop to 50%. Probably everybody will buy more DCAC panel. So then when the percentage of cost of the DC devices in the total investment is increasing, the DCAC ratio will decrease. So this is if DC panel price will increase, the DCAC ratio will decrease. But for example, if the module price is declining, as I mentioned, faster than other devices like the transformer station or the inverter or cabling or the structure, it can be estimated that the DCAC ratio will increase at the same time. Also, there are seasonal tilted structures, so it means that some local guys have to go on the site and set the structure, the tilted structure, which is not automated, to a different angle. it is also affecting the OPEX side. If you have a high number of DC panels, you have high number of structures, so you have to use more workforces. Also module cleaning. If you have less modules, if you have less modules, this will certainly affect how many times and how many money, dollars, euros you have to spend on the operational cost. And also the components. So what components you're using can affect the DCAC ratio. Module degradation. If you have high module degradation, because you probably use that kind of panels, you probably will go with higher DCAC ratio to cover the loss from the module degradation. Or the inverter type. There are multi-MPPT inverters and there are single MPPT tracker inverters. It means that due to the mismatches that comes from the DC panels, the long DC cables and different temperature of the panels, different shading, different soiling on the panels, the multi-MPPT shows higher yield with the separated trackers, and it can boost the power. So it means that with multi-MPPT trackers, multi-MPPT inverters, you will have the same result with less DCAC ratio. Also, module type affect this. So like mono and bifacial affects this. So this was about the idea and the theoretical part of the LCOE calculation. Actually, this LCOE method and calculation is used in many countries. Although in some countries it is not that general to use, but probably in the future it will be more used than it is used at the moment. So let's see what will be the effect of the grid requirements, and especially the so-called RFG effect on the DCAC ratio for larger power plants. So the European Union introduced a new requirements, a new grid code, not a new grid code, a new regulation for generators. And in that regulations, the reactive power support, so the grid support, has a lot to make. So there are a lot of parts which it consists of reactive power support for the grid. And especially for Type C and Type D panels, more reactive power capability might be possible depending how the local country interpret the RFG. And as you can see, this is the table of or the graph how the reactive power and the Pmax is related. This is the general graph comes from the EU RFG. But let's see how the Greek RFG affect this. Even though, to my best knowledge, this is not the latest one, so it's still under discussion how it will be implemented. But for sure, there are the type A, B, C, Ds, which are different from each other. So we have especially we focus now on the type C and type D, which mentions that the voltage connection is below 110 kilowatt, but the power will be between 20 plus 75 megawatt. And also the type D, which will mean that it will be above or equal to 110 kilowatt, and the power will be above 75 megawatt. So there is a definition in the Greek Git code, which is, yes, I mentioned, still under consultant, that the max, what is the Pmax, and it means the maximum continuous active power, which doesn't say too much, but let's go just into more details. That actually the power generator, it says, should be capable of providing reactive power at maximum capacity at varying voltage at the connection point according to the VQ, so and the voltage and the reactive power and the active power profile specified in this figure. So it means that these are the boundaries that were given by the RFG, and this is actually the boundaries for the Type D power plant. So it's quite strict to have this requirement here. And let's see what would be the case with, for example, the Huawei string inverter. So these are the equations that can be used for different points, and we have 2 points, the minus 0.35 and the 1.1, and minus 0.35 1.0, which is this point, exactly this point. And the other point is the 0.2.0.9. And based on these numbers and using the capabilities of the inverter, the PQ curve of the inverter, we can estimate for the Type D power plant, so connected above 110 kilowatt and using more, having more power than, so the Pmax will be above 75 megawatt. There can be the case when you have to use 15% more inverters added to produce the required reactive power. If we take into account an unload tap changer, the unload tap changer can help to cope with the changing voltage, the changing voltages online, it means. And then these numbers will change, and this can result in a better situation where usually the 8% more inverter might be enough for producing the required reactive power. And just to mention again, this is about Type D power plants, so large power plants, and this is just to show that this is how the Greek RFG affects the solar inverter design at this level, at this high power level. So this would be all regarding optimal DCAC ratio. So I hope it was useful for you, and please feel free to ask anything. So